Hey everyone there in Physics 40S land, it's Dr. Carroll. Welcome to our screencast, our first one of Unit 6. Unit 6 is all about electrostatics. I'm going to look at potential energy again, this time electric potential energy. So, when you think of static, as we looked at earlier in the course, we looked at static equilibrium, things not moving, everything balanced out, like if you're suspending a big screen TV on a wall, you have to have all the wires properly balanced, all the tension canceling out so that the TV doesn't move. That would be a moving picture, wouldn't it? In this chapter, we're looking at electrical charge staying relatively in one place. So buildup of charge, and that's what we get when we talk about static electricity, right? And in chemistry, we talk about an equilibrium, dynamic equilibrium, where molecules are moving back and forth between the reactant side and the product side. Things are still moving. Here we're talking about buildup of charge, talking about static as opposed to dynamic. In our next chapter, Unit 7, we look at current electricity, where particles are moving in a semi-organized way to create electricity. So, let's start at the very beginning here, and I got my little pointer to put a asterisk by the guts of an atom, the inside of an atom. There's lots of stuff, but we care about just the nucleus, where, among other things, we have protons and neutrons. Neutrons aren't going to be much of a focus in this chapter because they don't have an electrical charge, but protons do, a charge of +1 elementary charges. And the mass of a atom is focused within the nucleus, so it's got lots of mass, even though the volume is much smaller than that by the electron cloud around the nucleus. And electrons have a charge of -1, elementary charge units. So EC is the symbol we use for elementary charge. Some of you may remember coulombs from previous courses, and a Coulomb is 6.25 by 10 to the 18 elementary charge. So that's a really large unit. Take the reciprocal, 1 elementary charge is 1.6 by 10 to the -19 coulombs. So that is the conversion factor between them. And sometimes we'll talk about microcoulombs, pico coulombs, nanocoulombs, things like that. So here's a little chart of the subatomic particles. Sub meaning within, right? Like a submarine is something within the water. Marine meaning water, right? So subatomic within the atom. So we've got protons, which are P or P+, though you hardly ever see P+ written. 1 elementary charge, 1.6 by 10 to the -19 coulombs, and the rest mass for a proton is 1.673 by 10 to the -27 kilograms. You'd never have to memorize these numbers. Neutron, there's no charge, it's neutral, and so the mass, though, is allowed, and it's slightly more than a proton, 1.675 by 10 to the -27 kilograms. An electron has a charge of -1 elementary charge, so it's opposite charge of the proton, so -1.6 by 10 to the -19 coulombs, and the mass is 9.1 by 10 to the -31 kilograms, so around a 2,000th of a proton or a neutron. Okay? So let's continue on here and look at something you may have come across before, the basic laws of electrostatics. First is charge is conserved. If I comb my hair, which I do around once a month, I will transfer electrons from my hair to the comb. So I'm not creating new electrons, I'm just transferring from one place to another. So if it was 10 electrons transferred, I would have a deficiency of 10 electrons on my flowing black hair, as opposed to the comb, which would now pick up those electrons and have an excess of 10 electrons. Second point is the simplest fundamental unit of charge is 1 elementary charge. Okay, so you don't break up the unit of charge to anything less than 1 elementary charge. You don't have like a half of an elementary charge. You can have half of a coulomb, but a coulomb is lots of elementary charges, so that's a lot. Third one, like charges repel, opposite charges attract. Okay. Fourth one, charged objects attract neutral objects. So we have here a balloon, and we have here a wall, and then let's say you rub the balloon on your head and it picked up some electrons. So then the electrons would induce an attraction by pushing away the other electrons in the wall, leaving the protons close by, so you'd get an attraction between them. And if the attraction is strong enough, the balloon sticks to the wall. I remember as a kid going to a birthday party at my friend's place, and their father was putting up balloons, and rather than rubbing the balloon in his hair or using tape on his head, he used his underarms. And then they were giving out balloons at the end of the party, and I didn't take one because I mean he had put the balloon all over his underarm hair. So I figured, you know what, I'm just going to stick with the little puzzle or piece of candy, and someone else can have the balloons. Okay, aren't you glad you heard that story? Fifth point, electrons flow easily through conductors. Conductors like gold, silver, graphite is a conductor of electricity. Electrons, in the sixth point, electrons flow less easily through insulators, wool, wax, various plastics. So we have conductors, we have insulators, we can talk about conductivity and resistivity, and we will associate it with these things. And you always hear about conductors when you go into like Best Buy and they try to upsell you. When you buy a big screen TV, they say, oh no, that's not enough. You got to get the monster cable with a gold conduct thing. And really, can you really tell the difference? I can't tell the difference. So I can still see Tiger King just as well. I don't know what Tiger King is. I just saw that in the paper today. Okay. So let's do a bit of a unit conversion here, some practice, because we're going to see both coulombs and just numbers of elementary charges. So here's 55p. So that's 55 protons. Let's convert that to coulombs. Well, each proton is one elementary charge, so the proton symbol cancels, and one elementary charge is 1.6 by 10 to the minus 19 coulombs. So the elementary charge unit cancels. By the way, I'm on page 12 in our booklet, our Unit 5 to 8 booklet. We aren't using the mini text anymore. This booklet is a better way to deliver this content, I believe. So, of course, there's thousands of books about electrostatics. You can summon online, and of course go to our website and you can see videos about electrostatics. There's lots by a guy named Professor Dave. He's a good guy with physics and explains stuff very well, and he's got this catchy theme song at the beginning of his YouTube. Okay, so 55 protons, 1 EC for 1 proton, 1.6 by 10 to minus coulombs per EC. So 55 protons is equivalent to 8.8 by 10 to minus 18 coulombs. Coulombs given the symbol capital C. Next one, 3 by 10 to the 15th electrons. Convert that to microcoulombs. Well, one electron is inherently possessing -1 elementary charges. So we got 3 by 10 to the 15 electrons, -1 elementary charge per electron, and 1.6 by 10 to minus 19 coulombs per elementary charge. Now we want to get to microcoulombs. 1 microcoulomb is 1 by 10 to minus 6 coulombs. So we've used a chain of 3 conversion factors. Very popular way to answer these kinds of questions. And you get minus 480 microcoulombs. Okay. Next one, here we got Pico Coulombs, and we want to get to protons. So Pico Coulombs to protons. So we're going to know that 1 Pico Coulomb is 1 by 10 to minus 12 coulombs. 1 EC is 1.6 by 10 to minus 19 coulombs. 1 proton is 1 EC. Put that all together, and you get 2.9375 by 10 to the 7 protons. Okay, so that's just a bit of practice in terms of doing conversion factors. Good? Great. Okay, let's go to page 13 here. One way to electrify something is by friction. Okay, if you are bored today, you rub your socks against a carpet and then touch a doorknob, and then wash your hands after. This is going to cause a shock, right? So let's look here in the first example. Example 1, example 2. 2 by 10 to the 15 electrons are transferred from the hair to the balloon. We're back to this again, aren't we? Okay, so we want to calculate the Q on the hair and the Q on the balloon in coulombs and microcoulombs. Little q represents net charge. So the net charge on the hair and the net charge on the balloon. Now some of you may have seen Q used before for heat, and it is used for that as well. So just as we're learning a lot in science, one letter can be used like 4,000 different things, and letter Q is no exception. It can be used for charge, the net charge, and it can also be used for heat. So if 2 by 10 to the 15 electrons are transferred, then the hair now has lost those 2 by 10 to the 15 electrons, so it has a deficiency of 2 by 10 to the 15 electrons. So it has, therefore, a charge of positive 2 by 10 to the 15 elementary charges. And I can convert that to coulombs and then to microcoulombs. 3.2 by 10 to minus 4 coulombs or 320 microcoulombs. Why am I converting? Because that's what the question asked me to do. And then the balloon gains those electrons, so it's minus 2 by 10 to the 15 elementary charges times the conversion factor between Coulomb and elementary charges times the conversion factor between coulombs and microcoulombs. Or you could have very quickly said, well, if the hair is going to have a deficiency of 320 microcoulombs, then the balloon had to have an excess of 320 microcoulombs because you're transferring 320 microcoulombs. Some students ask, they say, well, how do you know that it's transferred from the hair to the balloon and not the other way? Because the question tells you it's transferred from the hair to the balloon. There are series, if you really get into this, you can start, what's the word I want? Ranking, that's it. You can start ranking different materials, what wants to give electrons to what. You can make a whole list of what kinds of plastics give to what other kinds of plastics, what kind of materials transfer electrons. And you can look that up if you want, but I'll just tell you in the question. Okay, the second example, we are, oh, maybe this is involved with some wine, right? Maybe you have a cork, and you know how sometimes the sommeliers, the fancy people who pour wine and stuff, they'll polish the cork with a cloth or something like that. So let's say you have 6 by 10 to the 4 Pico Coulombs transferred from the cork to the cloth. So the cloth wants, well, this just says this just says Pico Coulombs. It doesn't say whether it's electrons or protons. That's an interesting question, isn't it? Let's take a look here. So then the cork would lose 6 by 10 to the 4th picocoulombs of charge. Not electrons, but just picocoulombs of charge. So if that's transferred, then it's going to have, I guess we're going to think it's going to be protons. There's no reason not to, right? Negative 3.75 by 10 to 11 elementary charges, and the cloth is going to gain 6 by 10 to the 4 picocoulombs. Okay? Typically, electrons are transferred a lot easier than protons, especially in solid systems. But this question says that the cork transfers 6 by 10 to the 4 picocoulombs to the cloth, so it is now deficient in the positive charge, so it has a net negative charge of negative 3.75 by 10 to the 11 EC, and the cloth is positive 3.75 by 10 to the 11 ECs. Okay, so those are just straight friction examples. Let's talk about sharing charges by conduction. Okay, so I'm still on page 13 here. What if we have two charges, let's say two metal spheres, same dimensions, okay, and we bring them together so that they touch and then they separate. Okay, they're held on insulating plastic handles, so you don't get any grounding effect, you don't get any electrons transferring through you to the ground or any loss. So you just bring them together, the 9 microcoulomb and the 13 microcoulomb, you bring them together, and then you break them apart. So what's the final charge on each? All you're really doing is taking the average, right? You're taking 9 plus 13, so 22 microcoulombs of charge, and then dividing by 2. When you bring them together, the charges distribute themselves as far away from each other as possible. So sounds a little bit like Vesper, right, for you chemistry people. So 9 plus 13, 22 microcoulombs divided by 2. So the new charge on each is 11 microcoulombs. Second example, we have 5 microcoulombs on one charge, 8 on the other. Touch them and separate them, so the average is 6.5. And some kids say, no, you can't have fractions of charge. Well, hold on there. Yes, you can, because I'm not talking about a fraction of an EC. I'm talking about a fraction of a microcoulomb. Just like I can have a bagel, well, I can have half a... Yeah, I can have half a bagel, can't I? Okay, that wasn't the best example. I meant to say I can have a dozen bagels. I can have half a dozen bagels as well. So forget about that. There's holes in that theory, aren't there? So I got 6.5 by 10 to minus 6 coulombs. Well, I show you I can convert that, so I get 4.0625 by 10 to the 13 EC. So you can have fractions of coulombs, microcoulombs. You can't have fractions of EC. And both spheres don't have to be of the same charge. We see here in example 3, QA is 6 pico coulombs, QB is minus 9. Bring them together, take the average, so 6 and minus 9 is minus 3 divided by 2, minus 1/2 pico coulombs on QA, and minus 1.5 pico coulombs on QB. Okay? Now, what if you have 3 charges? Okay, so 3-point charges. So I got initially, I have a charge, so this is my initial, of 5 microcoulombs on A, 2 microcoulombs on B, and negative 4 microcoulombs on C. So I have 3 identically sized, in fact in the real limits of this it's like point charges. So identical point charges, but the amount of charge on these spheres is allowed to be different. So you have 5, 2, and minus 4. So now the question is the order of touching and separating going to matter? So suppose I take A and B, touch them together and separate. Then in the 3-step process, take A, which had just touched B, and now touch it to C and separate them, and then take B and C and separate them. So what is our final charges on each of these spheres? So A and B, you put them together. 5 and 2 is 7. Oh, now there's a phone, isn't there? That's great. I'm going to go to pause for a second here. Okay, I'm back. I want to make sure I'm recording. And yeah, I think I am. Pause, stop. Okay, let's keep going here. So, 3-point charges. So I bring the 5 and the 2 together, so that's 7 dividing at 3.5 on each. Then I have the A, which is 3.5, and I bring that up to C, which is negative 4, so that becomes negative 1/2 divided by 2, negative 0.25 on each. Notice I'm using something that's often used in physics and other areas of science, a little prime notation. And no, it's not derivative. I know some of you are taking calculus. It just means a change, so a new value. So if I put one little tick, I call it prime. A second tick, I call it double prime, so that's a newer charge. So now QA double prime and QC prime are both negative 0.25. And then I take the B, the most recent version of B, which is 3.5. Recent value of B is 3.5, and C is negative 2.5, so that's 3.25 divided by 2, 1.625. So my final values are A is negative 0.25, B and C are both 1.625. Okay, now If I did it in a different order, when I'm doing it over here, I go A, B, B, C, A, C. So A and B together, 7 divided by 2, 3.5, 3.5. Then B and C, so that's 3.5 and -4, so it's -0.5 divided by 2, so -0.25 on each. And then QA double prime is going to be my most recent value of C, which is -2.25, and A, 3.5 divided by 2. Sorry, 3.5 minus 0.25. So 3.25 divided by 2, 1.625. So A double prime, the final value of A, therefore, is 1.625. C is 1.625, but B is -0.25. So the final values on spheres A, B, and C depend on the order in which we do the touching and separating. Still, the conservation of charge works, and the value is, for the net charge, it's, let's see, 5 plus 2 is 7, minus 4 has to be 3. So if I take 1.625 times 2, 1.625 times 2, and minus 0.25, I get 3. So you're just shuffling them up, rearranging them in different ways. Let's do another example of that. This is on the bottom of page 13. So I have two different ways. I start with 5 on A, 0 on B. So B is neutral to begin with, and C is -3. So put A and B together. So 5 and -3 is 2. No, that was A and C. Start again. A and B together. 5 and 0 is 5 divided by 2 is 2.5. So A prime is 2.5, B prime is 2.5. And then I take A and C. So 2.5 and -3 is -0.5 divided by 2 is -0.25 on A and C. And then B and C is going to be 2.5 and -0.25. So 2.25 divided by 2 is 1.125. So Q A double prime is -0.25. QB prime, double prime, and QC double prime are both 1.125. Second example, I do B and C together, so I get -1.5 on each. Then the most recent value of B, yeah, I know that, that's -1.5. Most recent value of C is -1.5. Touch that to A, so take the average, 5 and -1.5, so that's 3.5 divided by 2, 1.75 on each. And then touch the A and the B together. So the most recent value of A is 1.75 and of B is -1.5. So I'm going to take the 1.75 plus 1.5 negative, divide by 2, and I get 0.125. Oh, I'm going to fill that in there, 0.125 for each. And notice, to check our work, the whole thing would have to add up to 2, because A is 5, B is 0, C is -3, so that's it up to 2. So 0.125 times 2 is 0.25 plus, what's the value for C? 1.75, so that gives me 2. And on the other left-hand one here, B and C are both 1.125, so that's 2. Let's see, 1.125 times 2. I should be better with my fractions, shouldn't I? 2.25, and well, how can that be 2? Something's odd here, isn't it? Let's look at this again. 5 and 0, take 2.5 on each, and then A and C, so 2.5 and -3. 2.5 minus 3, divide that by 2, -0.25. And then my B final and my C final are both 1.125. So 1.125 times 2 is 2.25. A is -0.25, so minus 0.25, and it works to get 2. So that's That's how that's going to work. And so now, by the way, if I took all three charges and touched all three of them together and then separated them, that would be the final values. You would just divide each by 3. So expect on a quiz or a test somewhere down the line a question where you have to do this steps of the separations. Okay, so now let's continue and let's look at something known as Coulomb's law. Just want to make sure I'm still recording, because if I'm not, I will get aggravated. No, good. We're still good here. So page 14, Coulomb's law, named after this guy, Charles d'Augustin Coulomb, some fancy name. And what Coulomb discovered is the Coulomb force. An electrostatic force could be an inverse square law. Just like we looked at gravity, an inverse square law, force of gravity is capital G, m1, m2 over r squared. The electric force is something known as Coulomb's constant times the charge on A times the charge on B divided by the distance between point A and B squared. And we use r for distance, which is annoying. If you want to use lowercase d for distance, go ahead. Most people use r for distance. So Coulomb force is the electric force, electrostatic force. You hear all those synonyms. Force Coulomb, force electric, Fe, Fel. I mean, we aren't talking about elastic forces here. So if I write El in this chapter, I'm talking about electric, not elastic. Okay? So here we see the equation. The electric force is K, known as Coulomb's constant, which is 8.99 something or other. We round it to 9 by 10 to 9 newtons meters squared per Coulomb squared, times the charge on A in coulombs times the charge on B on coulombs divided by the distance in meters between them squared. So the greater the charge, the greater the force. Increase the charge in both of them, increase the force by the proportional same amount. Farther away the charges are from each other, the less the force. Okay? So, and most books do what I'm doing here, taking the absolute value of the charges, so you don't talk about negative forces. It's still a vector, but we'll take care of the directions as we go through each question. So let's go to the first example here. We have a charge A, which is 3 coulombs, and a charge B, which is 5 coulombs, and they're 4 meters apart. So we want to calculate the net electric force on B due to A. So A on B. So what you do is you pretend that A is not moving, but B is. They're both positively charged. So basic electrostatic laws say that B would be pushed to the right. Now, there's always the kid who says, yeah, but A is pushed to the left. And I go, yes, I know that A is pushed to the left, but that's not the darn question. The question says, what is the force exerted on B due to A? So the direction will be to the right. Take care of the directions first. Then plug in the numbers. So 9 by 10 to 9 Newton meters squared per Coulomb squared times 3 coulombs times 5 coulombs over 4 squared, which is 16 square meters. All the units cancel nicely, and you get the units 8.44 by 10 to the 9 newtons. 2 decimals is good enough to the right. B is pushing back on A with the same magnitude of force. Some kids think you divide by 2 or something. No, you don't do that. B pushes back on A with the same force, 8.44 by 10 to 9 newtons, and that's directed to the left. Okay? Next example, we got A and B with 2 picometers between them, and I direct them in a vertical fashion there. They're both negatively charged, so we want the force of A on B. So that means, well, A is negative, B is negative, so B is going to move down, assuming A is fixed. A on B, you got to look at every darn little symbol. So 9 by 10 to 9, take the absolute value. Oh, I did that in my head. 4 by 10 to minus 6 times 8 by 10 to minus 6 divided by the distance between them, 2 by 10 to minus 12 squared. And I get 7.2 by 10 to the 22nd newtons directed to the south. And as you can imagine, the force of B on A is going to be the same magnitude, opposite direction. So 7.2 by 10 to the 22nd newtons directed to the north. True north. Example 3. we have A and B, two charges. A is 5 microcoulombs, B is -6. So here they're opposite charges. They're 9 centimeters from each other. So the A is going to bring B towards it. It says, hey B, come my way. So 5 microcoulombs, B is directed to the left. The force of A on B is 9 by 10 to the 9th times 5 by 10 to the -6 times 6 by 10 to the -6 over 9 by 10 to the -2 squared. So 33.33 newtons to the left, and B on A would be 33.33 newtons to the right. Okay? Now we can get varieties of questions. Of course, here we have one where, example 4, where you're given the force, 6.5 newtons. A on B is 6.5 newtons, and that would be directed to the left if I wanted to look at the direction. And then I isolate for R, so R is the square root of K QA QB over force electric. So 9 by 10 to 9 times 4 by 10 to -3 times 8 by 10 to -6 divided by 6.5, and you get 6.66 meters. So given the force and the charges, you can get the distance between the two objects. As an aside, sometimes lowercase k isn't given as 9 by 10 to 9 newtons meters squared. What is it? Yeah, newtons meters squared per coulomb squared. Rather, it is given as 2.3 by 10 to the -28 newton meters squared per elementary charge squared. But that one is not used as often. Okay, on to the next example. Let's say we have two positively charged objects. They're 1 centimeter. Does that say 1? Yeah, that's a 1. Apart, and they're repelled by a force of 0.2 newtons. What is the charge on each? Okay, so, but the charges are equal. So, QA equals QB equals just Q. So, Q squared is force electric R squared over K. So, I want to, I'm given the force, it's 0.2 newtons. I'm given the distance between them, 1 by 10 to the -2 meters. I square that divided by K, and I get 4.71 by 10 to the -8 coulombs. Now, why does it say 7? One says 7, one says 8. Okay, we better double check this. Here we go. I'm going to take the calculator here, and I'm going to take 0.2 times 1 by 10 to the 2 squared divided by 9 by 10 to the 9, and then I'm going to take the square root of that, and scientific notation, it is by 10 to the -8, so then here this has to be 4.71 by 10 to the -8 coulombs divided by 1.6 by 10 to the 19 minus, and I get 2.95 by 10 to the 11. Okay, now I'm just going to open the door for a second because my dog is scratching to get in. Hold it. There you go. The dog was really interested in Coulomb's law because the dog thought I was saying Cauchy's law, right? Cauchy's law, not Coulomb's law. Okay? Oh, and there's the dog. Everyone say hi. This is Mercy. Hi, Mercy. How are you doing? Do you understand Coulomb's law? Sure she does. Okay. Oh, she just wants to hang out here. It's snowing outside today. Whatever the day it is, that's what it's doing. Okay. Oh, now we get fancy with 3 collinear charges. So, what if you have 3 charges? What do you do with cases like that? So, I have here, and this is on page 15, collinear means they're all in a line here. So I got 3 coulombs, 4 coulombs, and 6 coulombs. And the distance between A and B is 2 meters. The distance between B and C is 5 meters. And we want to find the net force on QB. So QB is the one in the middle in our question. So this is vector addition here, and I'm going to use rights and lefts. You can use east and west if you want. I don't want to use positive and negatives. I would rather use rights and lefts, but you could use positive and negatives if you want. So the net force on B is the force of A on B, and that's going to be to the right. And then you have the force of C on B, and that's going to be to the left. So A pushes B to the right, C pushes B to the left. My net force, well, let's see. A is closer than B, but it's a little smaller. It's just 3 coulombs, whereas C is twice as much charge, but it's 2.5 times away. So Coulomb's law is more important with the distance because there's a square term in there than with the charge. So you're going to have a battle going on here, but I think the right is going to win here. Well, let's see. So if I get the value to the right, I get 2.7 by 10 to the 10. 9 by 10 to 9 times 3 times 4 over 2 squared. And the left component, which is C on B, is 8.64 by 10 to the 9th. So now right is larger than left, so you just take the difference with the final direction being to the right. So my net force on charge B is 1.84 by 10 to the 10 newtons directed to the right. Okay? Now, the next part says, what about the net force on A? So the net force of A is going to be B pushing A to the left and C pushing A to the left. So they're both directed to the left. So my net force, oh, here comes my other dog. This is Lily. She's interested in this stuff as well. So the net force is going to be the left, and I just add up the two values. There was a power failure yesterday, and she's still scared from that. There's this knocking noise on the stove, motor stopping and starting that gets her. Oh, maybe that was the fridge motor. I don't know. There's so many noises going on. So she's trying to calm down today. So we got 9 by 10 to 9. Now B on C is going to be 4 times 3 over 2 squared. C on A, well, that's 7 meters apart. So 9 by 10 to 9 times 6 times 3 over 7 squared. So you add those together, and now the dog is lying on my cable. So thank you. That's great. 3.03 by 10 to the 10 newtons to the left. So notice the force, net force on A is not the same as the net force on B. The net force on C, well, that's different as well. So A pushes C to the right, B pushes C to the right. Some people think that somehow there's some blocking going on, that A can't see where C is because B's in the middle. No, just pretend that B's not there. When you want A on C, just go straight from A to C and get the force. When you want B on C, straight, not Beyonce, but B on C, it's to the right. So I add those together and I get 1.2 by 10 to the 10 newtons. Then example 2 is another collinear case where there's a charge in the middle which is negative, and I'm going to let you try that one on your own. Okay, and if you have questions, make sure to email me or SB me if you can't do that. Okay, then I'm going to page 16. Here's a right angled triangle, and I can get the net force on the vertex, this guy here, and that would be the only one I'd ask. So you have A on B is pushing to the left, and what's the other one here? C on B is pushing down. So you have one to the left, one down. So you get your components to the left, 9 by 10 to 9 times 4 times 8 over 3 squared. So that's to the left. And down you got 9 by 10 to 9 times 16 times 8 over 2 squared, 4. And then you just do your Pythagorean theorem, your angle, and you see that left, then 83 down. So you're being pushed somewhere like this, right? One's pushing down, one's pushing to the left. So your B charge is moving somewhere like that. And the last topic we look at for Coulomb's law is what's called the proportional Coulomb's law equation. So there's other configurations, by the way. There's like squares and more charges than that, but we can't look at every single possibility. Right angle triangle is as tricky as it's going to get. I mean, I could look at 4 charges collinear, but in terms of things off of collinearity, it wouldn't be, if that's such a word, it would be a right angle triangle. Okay. Proportional Coulomb's law equation is just if you know that by the proportions by which a charge changes, you can get the new force. So the equation, and you would be given this, well, actually you can memorize it, or if you need it, I'll give it to you. The new force is QA new over QA original, QB new over QB original, R original squared over new squared times F original. So it looks scary, but it's really not. Here's example 1. Suppose you're given that the original force is 1 by 10 to minus 5 newtons. So the question says, what happens if I change the charge on A, which was Q, right? It was Q. What if I change it to 2Q? So now it's 2Q over Q, so it's twice the charge. In other words, I'm doubling the charge on A, I double the charge on B. Sorry, I double the charge on A, I double the force. So my new force is 1 by 10 to minus 5 times 2, or 2 by 10 to minus 5 newtons. In the second example here, what if I decide to triple the charge on A? Like refresh, go to the beginning, and then triple the charge on A by going from QA to 3Q. So it's 3 times 1 by 10 to minus 5. So it's 3 by 10 to minus 5 newtons. Okay? The third one, what if I decide to make QB a value of 4Q? It was 2Q, but now it's 4Q, so it's been doubled. So my new force is 2 times the original, so 2 by 10 to the minus 5. Okay, and then I have a fourth example where it got cut off the boundary there, so don't worry about it. Let's go to page 17. Still the same charge, but here I'm going to do 2 things at once. I'm going to double. I'm not going to double. I'm going to make QA become 6Q. It was Q, so it is now 6 times. QB is now changed to 5Q, so that's started at 2Q, so that's 2.5 times more. So plugging into the equation, I'm not changing any of the distances yet. I'm going to get 6 times 2.5, which is 15 times the original force. So 1.5 by 10 to minus 4 newtons. So you can make more than one change at the same time. And you just multiply those proportional changes together. Now, in F, I'm going to change the distance to 0.2 meters. It was 0.1, so now I'm doubling the distance to 0.2. Doubling the distance to 0.2, so my force is now a quarter of what it was before. If you plug it into that proportionality equation, that's how it works. So 0.1 divided by 0.2 all squared, or 0.1 squared over 0.2 squared, you get the same thing, a quarter of F original. So, excuse me, 2.5 by 10 to minus 6 newtons. If I squeeze things closer together, it was 1/10 of a meter, and then I make it just 100th of a meter apart. So there I have decreased the distance by a factor of 10, so the force increases by a factor of 100. That's exactly what we mean by the inverse square law. So decrease the distance by 10, increase the force by 100. So it's 100 times the original force, so 100 times 10 to the minus 5, or 1 by 10 to the minus 3 newtons. And as you can guess, all the buildup is to part H here. What is my new force if I do 3 changes at once? So I make QA a third of what it was originally, so let me just say a third of Q. QB switches to 7Q, and R goes to 50 millimeters, which is 0.05 meters, right? So my new force is my QA new, so a third Q over my original QA, which was Q, times my QB new, which is 7Q, over my original QB, which is 2Q, times the original distance between A and B, which was 0.1 squared, over the new distance, 0.05 squared. Plug all that in, multiply by the original force of 1 by 10 to the minus 5 newtons, which is given, and you get 4.67 by 10 to the minus 5 newtons. So there you go. That is Coulomb's law, and look it over, and there'll be practice questions very soon on this. Okay? Have fun. My dogs say it's time that I have to take a break, so I'm going to take a break now.